Look around you for a second. The chair you're sitting on, the screen you're looking at, even the air you're breathing right now, what is it all actually made of? Welcome to this explainer. Today, we're not just doing a standard science lesson. We are taking a cinematic voyage deep into the hidden architecture of matter itself. Every single thing you can touch, see, or breathe is built on a glowing, vibrating foundation of pure energy and structure, and we're going to explore exactly how it works. Imagine taking an everyday object, like a glass of water, and zooming in. I mean, really zooming in. Past the liquid surface, past the microscopic level, straight down into the absolute fundamental building blocks. If you did that, you'd eventually hit something pulsing with unbelievable energy. For centuries, the greatest scientists and philosophers obsessed over one massive question. If you chop up a piece of matter again and again, what is the ultimate, absolute, tiny stopping point? The sheer scale we're dealing with here is honestly mind-bending. The word atom actually comes from the ancient Greek word atomos, which literally means indivisible. Those early thinkers, they truly believed this was the end of the line. You couldn't break things down any further. To give you a sense of just how tiny this universe is, millions of these magnificent, constantly moving structures can fit comfortably inside a single grain of sand. It's wild. Everything in the entire cosmos is basically built out of these invisible, microscopic bricks. So, how did we actually start decoding this hidden world? Well, we have to talk about John Dalton. He basically gave us the foundational blueprint of matter. He proposed that atoms are these ultimate indestructible particles. You absolutely cannot create or destroy them in a chemical reaction. He also figured out that atoms of the same element are completely identical. But the coolest part? They're highly social. They dynamically snap together in strict, fixed mathematical proportions to form molecules. Think of it like a cosmic collision. Picture exactly two glowing hydrogen atoms violently crashing into one oxygen atom, beautifully fusing to create a single molecule of water. But, science is this constantly evolving mystery. As our tech got better, we realized the atom actually wasn't indivisible after all. Enter J.J. Thomson. He unlocked the very first subatomic secret, the electron. He discovered these incredibly tiny, negatively charged particles and theorized they were just stuck inside this massive, glowing sphere of positive charge. People called it the plum pudding model. It was a massive leap forward at the time, but spoiler alert, it wasn't the final answer to our microscopic puzzle. Okay, picture this next moment in slow motion. Ernest Rutherford decides to test Thomson's model with his now legendary gold foil experiment. He fires a beam of positively charged alpha particles, think of them like tiny, powerful energy lasers, straight at an impossibly thin sheet of gold foil. He fully expected them to just tear right through the atom's glowing fog, and, well, most of them did. But then came the absolute shocker. A few deflected off course, and a tiny, incredibly small number violently bounced straight back. Rutherford later said it was as crazy as firing a 15-inch naval artillery shell at a piece of tissue paper and having it bounce back and hit you. So, what did those dramatic bounce backs actually mean? Well, they literally changed physics forever. Rutherford realized that the atom is definitely not some solid sphere of pudding. In fact, it is almost entirely empty space. All of that positive charge and nearly all of the atom's mass is hyper-concentrated in this incredibly dense, powerful core, right dead center. He named this glowing heart of the atom the nucleus. With that discovery, we can now decode this cosmic architecture into the three main subatomic particles that build, well, you. Deep inside that super-dense nucleus, we've got protons, which carry a positive charge, and neutrons, which carry absolutely no charge at all. Both of them have a mass of roughly 1 atomic mass unit. Then, way outside that nucleus, orbiting in the vast empty void, are the wildly fast, negatively charged electrons. And these guys, they have practically zero mass compared to the heavy lifters sitting in the core. But hang on, Rutherford's model had a massive flaw. According to classical physics, if negative electrons are orbiting a positive nucleus, they should constantly lose energy, spiral inward, and collapse the atom instantly. Poof, gone. To solve the mystery of why atoms, and therefore you and I, don't just spontaneously collapse out of existence, Niels Bohr stepped in. He proved that the atom features this brilliant futuristic architecture where electrons orbit in perfectly stable glowing circular paths called shells. They don't just lose energy and crash, they lock into these tracks perfectly. And nature relies on a brilliantly elegant mathematical rule to govern these shells. It's the formula 2n squared. In this equation, n simply represents the shell number as you count outward from the nucleus.
This incredibly sleek little formula dictates exactly how many electrons can legally fit into each specific orbit. It is literally the universe maximizing stability through pure mathematics.
When we plug numbers into that cosmic formula, we unlock the fixed capacities of these energy shells. The very first orbit, nearest the nucleus, the K shell, is tiny, so it holds a maximum of just 2 electrons. Moving outward, the L shell holds up to 8. Step out again, and the M shell expands to hold 18. These glowing energy rings fill up systematically from the inside out, establishing the ultimate particle rules for how elements will interact with each other in the real world.
To truly master this atomic world, we have to know how to measure it. Every single atom has an atomic number, represented by the letter Z, which is simply the total number of protons it has. Think of it as the ultimate ID badge for an element. But then we also have the total mass number, represented by A. Since electrons weigh basically nothing, the mass number is just the sum of your protons and neutrons, all securely locked together inside that central nucleus. Now, things get super fascinating when nature decides to bend its own rules. Sometimes, atoms of the exact same element can actually have a different number of neutrons packed into their core. We call these isotopes. And the contrast in their stability is crazy. Take carbon-12, 6 protons, 6 neutrons, perfectly stable. But then look at carbon-14, 6 protons, but 8 neutrons. Those extra heavy neutrons make it a radioactive isotope. It gives us this wild duality between a perfectly stable building block and a radioactive timer that scientists literally use to precisely date ancient fossils. And the instability of those radioactive isotopes isn't just some neat trivia fact. It is literally the glowing engine driving modern technology. When you split or combine these heavy, unstable nuclei, you release a breathtaking, almost terrifying amount of energy. We use uranium to power massive nuclear reactors that keep the lights on in our cities. Scientists are looking at elements like thorium to build the high-efficiency energy grids of tomorrow. And right now, in hospitals all over the world, targeted radioactive isotopes are being used as advanced, life-saving medicine to seek out and treat diseases like cancer. So we just saw isotopes, but nature has another awesome trick up its sleeve called isobars. Unlike isotopes, isobars are atoms of entirely different elements that astonishingly share the exact same mass number. Let's look at calcium and argon. Calcium has 20 protons. Argon only has 18. They look completely different, they act completely differently in the universe, but because of their specific number of neutrons, they both weigh in perfectly at a mass number of 40. It's a cosmic coincidence. Which brings us to the absolute driving force of all chemistry, valency. Valency is basically an atom's combining capacity. Take hydrogen, for example. It has a valency of exactly 1. It's only got 1 electron in its outer shell. And here's the secret to the universe. Atoms desperately crave stability, so they will dynamically trade, steal, or share electrons just to achieve a full, happy outer shell. Hydrogen has a valency of 1, oxygen has a valency of 2, because it needs 2 electrons. This desperate, non-stop quest for electronic stability is the singular reason atoms violently crash together to form every molecule in the universe. As we wrap up this explainer, I want to leave you with a thought that kind of makes you question the very nature of the matter you're sitting on right now. We've taken this cinematic journey from the ancient Greek philosophers all the way down to Bohr's glowing futuristic shells. We know that everything is made of atoms, and we know from Rutherford that atoms are 99.99% empty space. So, if the chair you're sitting on, the screen you're looking at, and the actual body you inhabit are almost entirely empty space, what unseen forces are truly holding your reality together? Think about that microscopic energy the next time you look at something as simple as a grain of sand. Keep questioning, guys, and stay curious.